In this video, we're going to discuss what the graphs of inverse functions look like in relation to each other. So if we graph a one-to-one function and then we graph its inverse on the same set of axes, what we'll see is that the two graphs are reflections of each other over the line y equals x. And it's the line y equals x because of the fact that we took the x and y coordinate from each point on the original and switched them to get the points on the inverse. So we're going to look at a few examples of some pairs of inverse functions we've discussed in previous videos. So one pair of inverse functions we looked at was x cubed and cube root of x. So I'm just going to graph those real quick on this set of axes. I have the points written down there that I'm using to do that. There's my best attempt drawing on this tablet for x cubed, and then cube root of x is going to have some of those points in common. And we'll use a couple others as well. That one was much easier. Alright, so what we said is these graphs are reflections of each other over the line y equals x. I'm going to draw that line in for us in green here. I'm just going to draw it as a dashed line. So the line y equals x is going to have all the points where y and x are equal. So 1, 1, 2, 2, 3, 3, 4, 4, and so on. Alright, so what we're seeing here then is the red and the blue graph are reflections of each other over the line y equals x. For example, the point 2, 8 up here and the point 8, 2 here are reflections of each other over that line. And so are all the other points on that part of the curve. Same down here. Negative 8, negative 2, and negative 2, negative 8 are reflections of each other over that line. So are all the other points on that branch. And then even in here you can see that the red and the blue are reflections of each other over that line. The points that the functions have in common lie on the line. So negative 1, negative 1, 0, 0, and 1, 1 are all on the line. So those points don't get reflected because they're on the line. That's why the functions have those in common. Here's another pair of inverse functions we looked at. We started with square root of x plus 5. We found its inverse function, which required restricting the domain on a quadratic. And we're going to see here just another reason why that's important, that restricting of the domain. So let's graph these. So there's the square root function. And there's its inverse, which was the right half of a parabola. We chose the right half so that the domain of that half a parabola was the same as the range of the inverse. And we can see that that was the correct choice when we look at the relationship between these graphs. They're inverses, so they're reflections of each other over the line y equals x, which we can see once we draw that in. So those points negative 5, 0 and 0, negative 5, for example, are reflections of each other. The graphs meet here at a point on the line, so that's the point they have in common, and the rest of the shapes are reflections of each other over the line as well. We saw an example in a previous video of a function that was its own inverse, and it was this rational function here. And if you're not familiar with rational functions, they often have asymptotes, which are just lines that the graph approaches without touching. So this graph has a horizontal and a vertical asymptote that it approaches. And I plotted a couple points there, but this graph, we said this function is its own inverse. So since it's its own inverse, what that means is the graph of this function is going to be symmetric over the line y equals x. Because if we reflect each point on that graph over the line y equals x, and we do that for all the points, we get the exact same graph because it's its own inverse.